Welcome to this Scikit machine learning tool tutorial. In this video, I'll walk you through how we use random forest regression enhanced with physics-informed features to predict creep rupture life in stainless steel. We will explore how this method combines machine learning with physical understanding to improve predictions in material science. Physics-informed machine learning, or PIML, integrates known physical laws and domain knowledge directly into the machine learning process. This is especially helpful in scientific fields, where models that ignore physics may produce results that look good statistically but don't make physical sense. PIML helps models stay grounded in reality, and it often allows us to achieve strong predictive performance with smaller datasets. There are three primary ways to apply physics-informed machine learning. First, through physics-informed feature engineering, where we include inputs that are based on physical laws, equations, or domain-specific metrics. Second, by using physics-informed loss function, which penalize predictions that violate known physical constraints. Third, by designing model architectures that inherently respect physical symmetries or behaviors, such as enforcing conservation laws or known functional relationships. So, what is the creep rupture test? The creep rupture test is a high-temperature mechanical test used to assess a material's ability to withstand long-term stress. A cylindrical specimen, often threaded at the ends and reduced in the center, is subjected to constant tensile stress at a fixed elevated temperature for hundreds or even thousands of hours. We record the time it takes for the sample to rupture, which tells us how the material behaves under prolonged heat and load, critical for components used in power plants, nuclear reactors, and aerospace. In this project, we applied physics-informed feature engineering in two key ways. First, we calculated the stacking fault energy from alloy composition using semi-empirical equation, since stacking fault energy influences how material deforms. Second, we created the PI creep feature, which is the log base 10 of the estimated creep life from the Manson-Hayford time temperature parameter model. These features bring decades of known domain knowledge into the model in a form that machine learning can easily use. Our dataset is based on creep test data for SS316 stainless steel, one of the most widely used high-temperature alloys. Each sample in the dataset contains 20 input features, including the elemental composition, mechanical properties like stress and temperature, and two physics-informed features we just described. The target variable is the creep rupture life in hours. These features form the input to the random forest model we're about to train. A random forest regressor is a supervised ensemble learning model that predicts continuous values using a collection of decision trees. Here's how it works. It builds many decision trees, each trained on a random subset of the data. At every split within each tree, only a random subset of features is considered, which helps introduce diversity among the trees. Each tree makes its own prediction for a new sample, and the final prediction is simply the average of all these predictions. This approach reduces overfitting and improves the model's ability to generalize. We split the dataset into 80% for training and 20% for testing. Using the Scikit web interface, we train the random forest model without input features. Once trained, the model predicts the creep rupture life for the test set. We evaluate the model using coefficient of determination, also known as R-squared, which tells us how well the predictions match the actual values. A higher R-squared value means a better fit. This is our Scikit ML AI interface. You can write down the project name here and also add the description of the project. So this is a demo of using Scikit ML AI interface to implement physics-informed machine learning with random forest regression model. we demonstrate that creep rupture data with physics-informed features will help the machine learning model make better predictions by comparing the R-squared values of the model predictions with and without the physics-informed features. So we will compare the two datasets. The first one is without physics-informed features, and the second is with physics-informed features. Next, let's select our dataset. There are 4 choices on the data type drop-down list: tabular, image, text, and signal. We choose tabular since our dataset is in CSV format, and we choose Upload CSV and click this button. We choose SS316 dataset. This dataset does not have physics-informed features. Let's see how our model predicts with this dataset first. We choose creep rupture life as our target, and we choose machine learning algorithm, and we select random forest regressor as our model. And we choose R-squared as our evaluation metric, and we click Perform. You can see the model has R-squared value of 0.8. It's not very high. It means the model does not make prediction very well. Now, let's choose the dataset with the physics-informed feature. We choose tabular, upload CSV, and click this button again, and choose PISS316 dataset. Here, you can see we have the stacking for energy and the PI creep feature. These 2 columns are our physics-informed features. The same thing, we choose creep rupture life as our target. And then we choose machine learning algorithm. And also we choose our random forest regressor. And here we choose R-squared for evaluation, and we click Perform. Now we have R-squared value of 0.94, which is very good. Compared to the previous prediction with R-squared equal to 0.8, the dataset with physics-informed features provide more information about the physical reality and helps the random forest model make a better prediction. Thanks for watching.